In a previous video, we looked at how to conduct a two-sample z-test for comparing two population proportions. In that example, we looked at the scenario where GM was trying to see if there was a difference between a financial incentive and traditional methods in inducing people to quit smoking. We are going to use that same scenario, but now we're going to build a two-sample z confidence interval to compare those two population proportions. That is, we're going to identify a range of plausible values for the true difference in those population proportions, or a range of values for the difference in the true population proportions. So, to remind ourselves what the scenario is, in an effort to reduce healthcare costs, General Motors sponsored a study to help employees stop smoking. In the study, half of the subjects were randomly assigned to receive up to $750 for quitting smoking for a year, while the other half were encouraged to use traditional methods to quit. Of the 878 volunteers, none of them knew there was a financial incentive when they signed up. So it was only after they signed up that there was an assignment to either the financial incentive or the financial rewards group or the traditional methods group. At the end of 1 year, 15% of those in the financial rewards group had quit smoking, while only 5% of those in the traditional group had quit. In our last video, we compared these two sample proportions of 15% and 5% using a two-sample z-test for proportions. We found a big effect and we found a small p-value, and we said that there was overall strong evidence to suggest that financial incentives help people quit smoking. What we would like to do now, however, is build a two-sample confidence interval to compare the proportions. So say we didn't have any preconceived idea, or we didn't have a specific idea of what that true proportion or that true difference would be. For the hypothesis test, we were hypothesizing that there was in fact no difference in proportions, and that hypothesized value therefore was 0. But say instead we're interested in identifying a true value for the effect, or that is, what are plausible values for the true difference. And so we don't care whether that difference is 0, we just want to know how big the difference plausibly may be. And we don't care whether it's specifically 0 or not. To do this, we would use a confidence interval. So what I have done is I've pulled over from our previous work the definitions of pi 1 and pi 2, the two population proportions. So pi 1 and pi 2 are the true chances or the probabilities of quitting smoking under a financial incentive and the traditional methods respectively. These are the exact same definitions from the previous video that we used for our population parameters. That is, pi 1 is the true probability of quitting smoking under the financial incentive, and pi 2 is the true probability of quitting smoking under the traditional method. I have also pulled over the conditions required for a two-sample confidence interval to be valid. These are the same conditions we identified when we worked on the sampling distribution for the difference in sample proportions, and these are the same conditions required for us to be able to use a z interval. So we have to have independent samples, and this was satisfied because we had a random assignment to the groups. People were only assigned to either the the financial incentives group or the traditional methods group. We have random samples because people were randomly assigned to one of the other groups. And we have a categorical response and categorical explanatory variables because smoking or quitting status after 1 year is categorical, and the incentive is also categorical. People can either be assigned a cash incentive or a non-cash incentive. And finally, there are at least 10 successes and 10 failures in both of the groups, the financial and traditional methods groups, because there were 15% because 15% of those in the financial rewards group quit, meaning 15% of the 439 people in that group, or 66 people quit, and that also means that the remainder of those people, 373 people, did not quit. Similarly, we saw that 5% of the people in the traditional methods quit, and 5% of 439 is 22 people, and the remainder, or everyone else, is 417 people, and both of those are greater than 10. So we've satisfied all the conditions required to be able to use a normal distribution with a true population mean, a mean or a center of the true difference of pi 1 minus pi 2, and a standard error of the square root of pi 1 1 minus pi 1 over n1 plus pi 2 1 minus pi 2 over n2. So we are now going to be interested in building our confidence interval. Now remember, the form for any confidence interval is statistic plus or minus critical value times the standard error of that statistic. What we need to do now is identify what these three values are. We're trying to estimate or come up with a range of plausible values, the true difference pi 1 minus pi 2. That is, what is really the difference between the proportion of people who quit smoking with a financial incentive and those who quit smoking without a financial incentive? We don't know. All we have are the 800 some people who are involved in this particular study. This is not everyone at General Motors who quit smoking. This is not everyone in the population this is not everyone at General Motors who is a smoker, and this is certainly not everyone in the population of all people or at various companies who are smokers. So all we have is this small sample, and we're trying to estimate based on this sample what the true difference in these proportions are. And from that, we might be able to estimate whether it's worth using a financial reward to try to induce people to quit smoking. Maybe that little bit of extrinsic motivation of the financial reward is enough to get more people to quit smoking for long enough. So, our sample statistic, our best guess for the true difference, pi 1 minus pi 2, is our sample difference in proportions, p1 hat minus p2 hat. This is the same estimate that we used in calculating our z-test statistic. In our case, p1 hat and p2 hat are the 0.15 and the 0.05. 15% of people in our sample quit smoking when they had the cash incentive, and only 5% of the people in our other sample quit smoking when they did not have a cash incentive, or that is when they were quitting smoking, or they were trying to quit smoking with just traditional methods. So in our sample, we had 15% quit with the financial reward and 5% without the financial reward. Because these are our sample statistics, those are our sample proportions. We also need a critical value. We are going to build a 95% confidence interval. Our critical value is based on our confidence level and our confidence level only. Because we are comparing proportions and because we've satisfied all the requirements, namely the 10 successes and 10 failures requirement in each group, we are going to use a z-star critical value. So because we can use the z distribution and because we want 95% confidence, this z-star is going to be 1.96. There will be an upcoming video that shows you how to find both p-values and critical values for a 2-sample z-test or 1-sample z-test for comparing proportions. This comes from the JUMP calculator. The last bit that we need, we have our statistic, we have our critical value, is that we need the standard error of our statistic. So that is the standard error of p1 hat minus p2 hat. We saw in a previous video that the standard deviation of our sample statistic when we have independent samples should be the square root of pi 1, 1 minus pi 1 over n1 plus pi 2, 1 minus pi 2 all over n2. The problem is we're trying to estimate the difference pi 1 and pi 2. If we knew what pi 1 and pi 2 were in order to calculate our standard error, then we would also know exactly what that difference pi 1 and pi 2 is. So we don't know pi 1 and pi 2. That's why we have statistics. If I knew my parameters, this whole field would just be meaningless. So instead, because pi 1 and pi 2 are unknown, we use estimates. So we're going to use p1 hat and p2 hat as our estimates. So our standard error is going to be the square root of p1 hat 1 minus p1 hat over n1 plus p2 hat 1 minus p2 hat over n2, and it's the square root of that whole sum. We do know p1 hat and we do know p2 hat, and of course we have n1 and n2 because those are the sizes of our two samples. So I can use all of this and plug in. So I've got 0.15, 1 minus 0.15, all over 439. And then I've got P2 hat is 0.05, and I can plug in 1 minus 0.05, or 1 minus 0.05 over 439 for N2. When I work all of this out, my standard error is 0.02. Please note that the standard error for my confidence interval is not the same equation as the standard error for my hypothesis test. For my hypothesis test, I pool my information together because I'm assuming pi1 and pi2 are the same for a hypothesis test. Please go back and watch that previous video to understand that. In this case, all I want to do is estimate what that true difference is, and so I have no prior assumptions about what pi1 and pi2 are, so I am going to keep p1 hat and p2 hat separate, and I'm not going to pool my information together. So now I have my statistic, my difference in sample proportions, my critical value, my z-star, which comes from my jump distribution calculator, and the standard error of the difference of my proportions, which is calculated to be 0.02. So my 95% confidence interval for the difference of in my population proportions for pi1 minus pi2 is going to be is going to be 0.1 plus or minus 1.96 times 0.02. And that works out to give me a lower bound of 0.0611 and an upper bound of 0.1394. I'd like you to pause this video for just a moment and come up with an interpretation for what this means, and also identify whether these data are compatible with a large or a small effect. What I got for my interpretation is that with 95% confidence, the difference in true proportions of people who quit smoking with and without a financial incentive is contained by the interval 0.0611 up to 0.1394. The data are compatible with an effect. This whole interval is positive, and so this is supporting the idea that on average we are going to see more people quit smoking, or a higher proportion of people quit smoking when they have a financial incentive than when they don't. And this is a fairly narrow interval. The difference is only about 7 percentage points. This is a narrow interval because we have such a large sample. There are only 878 volunteers, meaning of 439 people in both of those groups. So because we have such a high such a high sample size in both of those groups, we are getting a very narrow interval, giving us a small standard error, and we're getting pretty precise estimation of what that true difference actually is. So we're getting a pretty narrow interval, and we're getting a pretty good idea of low variability around our effect size. So we're not getting a wide range of plausible values for that true difference of our proportions. Furthermore, we're getting a pretty decent idea of what that effect is. The smallest plausible value for the true difference is 0.06. So the smallest effect supported by our data is a difference of 6.11 percentage points. So on average, our data support an improvement of 6 percentage points more people quitting with a financial reward than without. The largest effect supported by our data is a difference of nearly 14%, of 13.94 percentage points. So that means that our data support an improvement of 13.94 percentage points more people quitting with a financial reward than without. I would say even the smallest effect If we have even 6 percentage points more people, if with a financial incentive there are the probability of quitting is 6 percentage points higher than without the financial reward, that's a pretty good gain. And if the largest effect is an improvement of 14 percentage points higher with the financial reward than without, that's certainly a big effect. So our data are supportive not just of an effect, but of a meaningful effect. So that is a completely worked example of building a two-sample Z confidence interval when we're comparing two groups. So in order to compare two population proportions, the first thing that we really ought to check is the nature of our variables. We have to have a categorical response because otherwise we can't find proportions, and we must have a categorical explanatory variables because otherwise we don't have two groups to get the proportions from. The next video will be short, and as I promised, it's going to show you how to find those critical values and p-values using JMP. I'm going to use the same example, the Cash for Quitters example, as the context so that we will find the p-value and the critical value for this scenario.